right, we'll get started. Thank you all for coming. This is the thesis defense of Joe Wilder in the Department of Computer Science. He has successfully defended his thesis proposal last week, so this is the next to last step in finishing things. So what we'll do is Joe will talk for 40-45 minutes. Afterwards, we'll have questions. I'll ask the committee to hold their questions for afterwards, because we will have plenty of time to ask the questions we want. After the question session in here, we'll ask everyone to leave except Joe and the committee members. We will have our opportunities to then ask the questions. And then after we have a discussion, we will send you out of the room, and then we'll come back after that. So with that, I will turn it over to Joe.
All right, thank you everyone for coming. Today I'll be going over my thesis defense, where I will be talking about generalizable bathymetric lidar representation learning using self-supervised retraining. So to kind of first, I want to talk about the data that we're working with. What is bathymetry? We can just think of it as the seafloor. So we're looking for a way to measure the space of the seafloor. And we do that using airborne laser bathymetry, which we can think of as just LiDAR. So it's typically operated from an aircraft or a drone, something of the sort, and it sends out pulses of light. And those pulses of light, it can record the land, and a special type of LiDAR is also able to get shallow, it's able to go through the water and actually get the bathymetry. So from those beams of light, you're able to get 3D coordinates, which from there you can then get a point cloud data structure. So this is the main data I work with here, LiDAR point cloud. Again, it's an unordered collection of three-dimensional points, which typically consists of just the X, Y, Z coordinate. But in addition to that, you can also have other things like intensity or the return number. And again, I'm working with coastal areas, shorelines, so it'll be representing the structure of the terrain. You can also assign labels to each point in the point cloud to get some kind of semantic meaning. So to kind of visualize what we're working with here, in the bottom right, you kind of have a reference image of a shoreline in Maine, and then behind it, you have the actual point cloud. So you have millions of different points. You can kind of see how it captures in the green, the land. You have that kind of ugly mixture of the blue and the red points, where the red is the bathymetry and the blue is the water surface. To get a better look at it, you can peel away the water. That kind of shows the bathymetry that we're going to be looking to extract with my methods. So looking at it from another angle here, you can kind of just see you've got the water surface, which is the kind of creates the boundary between the land and the bathymetry. A big problem with this data that makes it much more challenging is that you have a lot of noise points, which I showed here in the yellow. So that kind of hides away the true signal of the bathymetry. So you have to find a way to kind of cut through that. And you also have a lot of different edge cases. So whenever you come up with a method that is aiming to extract bathymetry, you have to make sure it can handle different things, such as like boats or trees. There's a lot of different things we'll see on the shoreline. So some different uses for this data, like what can we do with it? One big thing that NOAA does is they use it, they use the classifications to make digital elevation models. And from there, you can then do a lot of different things like flood modeling, so like understanding how the water is moving and the currents and stuff. You can also detect changes in the shoreline and do other coastal planning for like infrastructure. And another big thing is hazard detection and emergency response. When you use, like another way to detect bathymetry is with sonar, but it can struggle in the shallower areas. So it's kind of like the niche that LiDAR has. It's able to quickly, you can get a plane in the air and quickly scan the more shallow areas. So this is good. This is done already, but there are some challenges with the workflows to get the semantic understanding of the point cloud. And so that typically comes from a lot of the methods being designed for a certain area. But when you look at the distribution of the data across all the different locations, you get a lot of different conditions of the data, because you can have different LiDAR sensors that they might have different different ways to record the data. You also have different conditions with the water, so the turbidity of the water can kind of make it harder to get deeper bathymetry. Because of all that, some methods you typically have to tune different parameters manually for each area, which increases the amount of time you have to spend. Even then, after tuning it, a lot of the algorithms that are currently used, they still will have issues with the classifications. So you're still going to need to go in manually and correct them. And another problem is that a lot of methods are designed so that they're designed around the assumption that a point cloud is going to have bathymetry in it. But as you go away from the coast using LiDAR, eventually you'll get to the point where the LiDAR is unable to penetrate deep enough and get bathymetry. So you're just left with a point cloud of only the water surface. So a way to kind of filter that out would be nice. So the main objective I'm looking at here is if I can design a representation for bathymetry that transfers across different areas, different survey sites. So I want to see if I can maximize generalizability while also kind of balancing the effort that you have to put in. So can we avoid needing to tune something for every single area? So some traditional approaches that are currently done are, there's a lot of rule-based methods and statistical methods. So they kind of operate on human-made assumptions about the data that typically hold true. Some of those assumptions include clustering the points by depth. Like it's safe to assume that the water surface is going to be at like a set height. That's generally a safe assumption to make. You can also assume that bathymetry clusters around each other, but will be slightly less dense than the water surface because it's deeper. It's harder for the LiDAR to capture the bathymetry. Then another assumption is you have the noise you have to deal with. Noise, you can assume it's going to be sparse and that the signal is dense, but it's not necessarily always the case. So with that being said, these methods are good a lot of the time on simpler tiles when there's clean separation. But when you get to tiles that have kind of overlap between the water surface and the slope of the bathymetry, you can run into some issues. So here's an example of running some statistical methods on kind of like an easier tile. We have a histogram approach, which you can think of it as just like looking at the height levels of the bathymetry and just drawing a simple boundary. Everything under that boundary will be classified as bathymetry. So it's kind of, it has issues in that it assumes, you're going to have flat bathymetry and flat surface. It works okay in this case, but we'll see later it doesn't always work. And another one is just basic clustering. You cluster the data and you assume that the deepest cluster is bathymetry. But yeah, you go to run this on a harder tile, and of course the one-dimensional decision boundary is going to completely fail on something that has more complicated geometry, like that kind of slope. And the clustering one also, it can fail because it just can lock onto a cluster that doesn't necessarily capture the whole thing. And so the thing with these are, you could probably get it to work on this, not the histogram one, but with clustering, you could perhaps get it to work on that tile by tuning the parameters, such as the distance between, like you define a cluster by the distance between the points and how many points are required to be nearby to add it to the cluster. But again, another thing to pay attention to is that this tile is really weird. Like you've got kind of on the right here, you've got a cluster of noise points that aren't bathymetry. So that's going to trip up issues. That's going to trip up methods that rely on just clustering alone.
Just a quick question, Joe. I assume we're looking at like an XY square from the side, and so
Yes.
everything's been projected onto a single plane. So if there were a slope of true bathymetry, we would see like a large smear of points.
Depends on the slide, because I believe that this is a full tile, right? 500 meters.
Yes.
So, yeah, if you are looking at 1 meter, it's less noisy.
Yeah.
Okay. Thanks.
So to kind of summarize that, statistical methods, they're good on the easier tiles, but they struggle with overlapping planes. And again, when going from one area to another, you're probably gonna have to adjust the parameters that you use with the algorithms, which that requires manual effort. So to kind of move past that, we can look at neural networks. Neural networks have the potential to generalize better because they learn parameters from the data itself rather than us kind of telling it what it should be looking at. But a big thing is it depends on the data that you give the neural network. So just a quick kind of overview for neural networks. In this case, we can think of it as taking the point cloud as input. And so that will then go through the model, go through a series of transformations until it gets to the point of an output of guesses, where the guess is for every single point in that point cloud, what do we think that point belongs to? Like, do we think this point belongs to bathymetry or noise or whatever? And to get those guesses, that's the model, which is the weights inside of the model that make the transformations to the guesses possible. And we kind of train that model using a loss function, which is a way to, given what we expect is the ground truth data, what we expect is bathymetry and what is not bathymetry, and given what the model predicts to be bathymetry, we can then minimize the difference between those two outcomes. So the problem with point clouds is that it's an unordered collection of points. So you have to get a little bit more fancy with the neural network that you use. So some different models that kind of work with that is first PointNet. That's an older model, but it's kind of the foundation for a lot of the newer ones. The main signal for PointNet is that it just looks at the coordinates of each point and the global placement of each point. That's the main signal for that one. And a little later on, they came out with PointNet++, which is similar to PointNet. It again just looks at the global positioning of each point. But in addition to that, it also, for each point in the point cloud, it captures the neighbors around that point, and it uses something called max pooling to kind of get a summary of what is in that neighborhood around each point. So it then concatenates that to the global information, and it's able to make a better decision that way. Finally, dynamic graph convolutional neural network. That is the model I go with here, and the reason for that is because it kind of similar to PointNet++ in that it looks at the neighboring points, but instead of just going off of the coordinates of the neighboring points, it actually calculates a vector between each point and its 20 nearest neighbors. So from that, you're able to better capture geometry because you get if the different like the direction of each of the neighboring points and how far away they are. So you get some extra information there. So yeah, that's why I kind of start here with DGCNN. All of these neural networks have a similar high level kind of structure, and so they follow the pattern of using an encoder to make embeddings and a decoder. So the input, again, it will be the point cloud. To get more specific of the dimensions of the point cloud, you have n, which represents the number of points in a point cloud. Then you have k, which represents the number of neighbors for each point in the point cloud, which you can just, from what I've seen, they typically just use a value of 20. And then you have c, which represents the x, y, z coordinates. But again, you can also add more to that, such as the intensity, which is another feature that's returned from the LiDAR. So yeah, you take that as input, you put it into the encoder, and that converts the point cloud into an embedding, which we can think of as a higher dimensional kind of description of each point. So instead of just describing a point with the x, y, and z coordinates, you're describing the point with learned features from the training that will be done on the model later on. And then after that, you have the decoder, which will take those embeddings and it'll map each one to whatever kind of guess we want. In this case, it'll be whether a point is belongs to the bathymetry class or if it doesn't. So again, the big thing with neural networks, kind of the problem that is introduced with neural networks is that you need to find a way to get a large amount of data, and you need to make sure the data is diverse enough. Because to train the model, you need kind of a variety of different areas in the data set. So you need a way to kind of decide how many point clouds you need and how diverse is it. So that includes not just like having areas such as Florida and Hawaii, like different locations around the world, but there's also different LiDAR sensors that you want to make sure you include because from what has been seen in other research, you want to, the LiDAR can capture the data differently. So you want to make sure you're developing a method that isn't good on one sensor and then it kind of fails on a different one. So it's a way to kind of just increase the variety of data you have. So then one thing I want to kind of see here with this work is can we kind of minimize the amount of labels we need? Can we kind of avoid the pitfall of neural networks where you need a lot of, like a large amount of data? And going from that, can we then also utilize, point clouds that don't have any labels? Because, again, a lot of the labels that are out there currently are obtained from algorithms, which can have mistakes in them. So you can then end up with data sets that have incorrect labels in it, which can confuse the model. So if we could just train from unlabeled data, that could be potentially beneficial. So to do that, the main thing I want to look at in this research is self-supervised learning. The idea with that is instead of having a person go in or an algorithm go in and get all the labels for the data, the way it works is can we generate the labels out of the data itself? So that's the main thing I'm going to be looking at here. There's research on this applied to a lot of different things like large language models, protein sequencing, and it is also done in this kind of three-dimensional point cloud domain. But from what I've seen, it has not been applied to bathymetry yet. So to kind of give an idea of self-supervised learning, in this example, we have something called reconstruction loss. So this is kind of how large language models can be trained. The idea is you start with the raw data, in this case, a sentence, and you just randomly select some words represented by the bolded words there. You select those words, you mask them out, and you show the model that masked sentence with the kind of the gaps in it, and you ask it to predict what words it expects to be there. From that, you then, from the first sentence, you know what words are the ground truth, what you can expect to be there. You know what the model predicts. You take both of those and you can put it into a loss function. From there, you can then train the model on the unlabeled data. For my work, instead of using reconstruction loss, I went with contrastive learning. The way this works is you take the bathymetric point cloud as input, and you then go ahead and you want to just clone it. So you have the same point cloud twice. From there, you then apply some series of augmentations to both of those point clouds. In this case, in this picture, I just did a simple kind of flip, so they're facing different directions. But augmentations can also include things like jittering the points, so I kind of nudge them in a random direction, and it can include scaling the point cloud. So from there, you then have two different views of the same point cloud. After that, you then embed both of those different point clouds, and you then kind of go through the embedding of the source point cloud, and you kind of start picking different points, and the the kind of challenge here is you're asking the model to predict, given a point in this one view of the point cloud, can you then, given all of these potential candidate points on the cloned augmented point cloud, can you predict which point cloud matches up correctly in the opposing view? So what that is doing with the model is it's teaching the model that no matter what angle or scale you look at the point cloud, the point is still the same, even though you're changing the positioning of it or the rotation. So with that, you're able to kind of get an overview of what I want to be doing here. So again, the big benefit with self-supervised learning is you generate the labels out of the data itself. So we kind of start with phase one here, the self-supervised learning part. You're able to just go ahead and collect a lot of different point clouds, and you don't have to worry about labels at all. You don't have to label any of them. From there, again, with contrastive loss, you use the encoder to get an embedding for the point cloud, and you use those two embeddings, you put those directly into the loss function. And from there, you're able to train the encoder. And what I want to see is when we do that, what is it gonna learn? Is it gonna learn features that help with identifying bathymetry in point clouds, or what will it learn? So that's kind of what I'll be looking at. From there, though, you still have the decoder part of the model, which is not trained using self-supervised learning. So you do still need a smaller amount of labels to kind of instill the semantic meaning to map the embeddings from the embeddings to the class that you want to predict. So from there, we can kind of look at the data set that I use. Again, I want to make sure to include different survey areas, because the whole idea with this is if you can train a model on one area, like Florida or something, and then it's able to do good on Florida, that's good, but the real benefit, I would say, is can you then use that model in other locations? Because you don't want to, as you get new survey data in, you don't want to have to then go and retrain the model every single time for a new area. So for that, that's why I kind of choose 5 different areas. I try to include different sensors as well to see if it can handle different LiDAR equipment. And then I also include different levels of noise. In addition to that, I also make sure to include tiles that don't contain any bathymetry to better capture what we can expect to see in the real world. So the tiles, they start out as 500 meters by 500 meters. And again, I have the larger unsupervised set and the smaller supervised set. So for each survey site, I get two kind of data sets. So these are the 5 areas I picked. So at the top, we've got Louisiana, Florida, Hawaii, Maine, and Massachusetts. The first 4 locations I draw from to create a self-supervised learning unlabeled data set. So what I do is I kind of look at all of the tiles, the larger 500 meter by 500 meter tiles, and I extract smaller patches from each of the tiles so that it's easier to put into the model. So for each of the first 4 sites, I get 20,000 30-meter patches. That is what makes up the self-supervised learning data set. And then importantly, with the 5th site with Massachusetts, I don't include any of that data in the self-supervised learning data set. So Massachusetts will be kind of the true test to see if the model can work on something that has never been seen before. And then you get to the bottom, you have the fine-tuning data sets. So you have, for these, what I do is I pick 100 tiles for training, 50 for validation, and 100 for testing on Louisiana. So that'll be the training site. We'll train the model, the decoder for the SSL model, and we'll see if it can train on that and then test to the remaining 4 areas. So we'll see if it generalizes good to Florida, Hawaii, and Maine. And then we'll also see if it generalizes good to Massachusetts, which hasn't had any unlabeled data training. So just really quickly to go through a few of a few example point clouds from each of the areas. We have Louisiana, which there's not there's some complexity in it, like you have some slopes, but overall there's not a ton of noise. You see some noise with the water surface. We've got Florida. This is the oldest data I have in my data set. It's collected with a different LiDAR sensor. This one has a lot more noise in it, and it definitely has some strange shapes in the seafloor. Hawaii is an interesting one because it's by far like super simple. There's very little kind of variability in it. You just have these clear separations between the surface and the bathymetry. The only difference with this data is the distribution of the depth. This one uses a sensor that's able to go, a LiDAR sensor, and it's able to go much deeper. So you can see it gets down to around 30 meters. All of the other data sets typically are around 1 to 5 meters deep. So that's why I include this one. And then we have Maine. This data set is probably the noisiest, and it has, from what I've seen in the data, it also has some pretty sheer drop-offs, like almost like cliffs in the data. So the terrain's much more extreme in this one. And Massachusetts for the testing. This one, again, it's similar to what we've seen, but it does have some extra noise points in this one. So it'll be good to see, can the model cut through the noise on this data set?
Can I ask a quick question?
Yes.
Clarification.
Yes.
So you're training on just Louisiana, and then you're fine tuning on the other sides, and the real site is real test is Massachusetts. Did I get this right?
Yes, but I'm not. Well, I'm doing the unlabeled self-supervised training on the 4 sites, but I'm not fine tuning the model for the other sites.
Right, but so if like the main source of training is Louisiana, and you said Louisiana is an easy data set, how is this likely that then you'll be able to capture the way more complicated landscape of Maine if you just train on Louisiana? So I think I'm misunderstanding something.
Well, there are. I don't want to say it's only simple data in Louisiana data set. There are some complex, more complex point clouds. Yeah. So from there we can get to the self-supervised learning training. So again, we use the contrastive loss info NCE. We input the cloned point cloud and the source point cloud, train the model that way. I use an NVIDIA GeForce 5090, trained for about 200 epochs. Took about a day, and I found the best loss around epoch 134. So now there's a lot of different ways to tell if the training was successful. That'll be kind of by testing on those other data sets if it did good. But before we get to that, we can kind of do a visualization on the embeddings themselves by projecting them to 2D using a t-SNE plot. So you have this input point cloud here with the ground truth data labeled over it. Before self-supervised learning, of course, it's just a random encoder, so that's going to be kind of the starting point there. But after you do self-supervised learning, you can see that the red bathymetric points are kind of forming on the right, while the non-bathymetric points are being pushed to the left. So that shows promise that perhaps there are features being learned that will assist with the identification of bathymetry. So at this point, we do the fine tuning. So again, for SSL, this is just to train the decoder. So we use the tiles from Louisiana not to train the encoder, but just the decoder. And so we use the train validation test split, load the weights from the first SSL training phase, and again, to help with generalizability so that it can hopefully see other areas better, I do augmentations like jitter, rotation, scale again. And from there, we kind of get to a comparison experiment here. So we have the same DGCNN model for both the baseline and the SSL experiment. They both use the exact same Hawaii or Louisiana labels. The main difference is that we're trying to see here, does using that unsupervised data help it generalize better? Does using self-supervised learning, in the case of using a low amount of labels, help with the generalizability to the unseen locations? So to kind of go over some of the metrics to describe how good the model does, the main thing I use here, we do have accuracy, but that can be misleading sometimes. So I include F1, which is kind of the combination of precision and recall. So it's kind of a way to make sure we're minimizing the false positives while also minimizing false negatives while minimizing the false positives. That's kind of a way to, so F1, you can kind of just think of it as a way to identify, kind of maximizing the score for if we're able to correctly identify which points are bathymetry, like how many of them do we find and how accurate are we when we guess them. Intersection over union, it's mathematically pretty similar to F1, but it better captures the overlap, the actual shape, if it matches what we expect the predictions to be. So when training both of these, you can see the SSL model has a better starting point because it had the unlabeled data. We're training the baseline to see if it can do good on the Louisiana data, and it is able to, it's a bit more jumpy, it has to kind of learn from scratch. But it does overall go pretty quick, but it takes a bit longer to kind of converge. So here we get to the comparison, if SSL is helping to generalize based on one survey site. The first thing to pay attention to is that it does like around 1% worse with the accuracy on the baseline. So the reason for that is we're training the baseline specifically using Louisiana data. It's optimizing completely for that data. And the SSL model, it's only using the features it learned about bathymetry from self-supervised learning. So you then go from there and you look at other areas, and you can actually see that there's a much larger improvement using this self-supervised learning, which kind of makes sense with these other three areas, because the model did see this data in an unsupervised manner. But the real test to look at here again is Massachusetts. Does the unlabeled data help with seeing completely new areas? So neither of the models were able to see this one, and still it gave an improvement of nearly 7% accuracy. In addition to that, I want to see if the embeddings that we get from self-supervised learning, does it help not just with segmentation of the point cloud? Can we also use it to identify on a global level the tiles, if it has bathymetry or not? So what I did here was I swapped out the decoder to also, instead of outputting a prediction for every single point in the point cloud, I instead kind of summarize over all of those embeddings using max pooling to get a summary of the entire point cloud. And I use those embeddings to train the decoder to just output a single does this tile contain bathymetry or not? You can see here the self-supervised learning method. It was able to, even on the Louisiana data set, it actually improved performance. And on the test data set, it did a lot better, which shows that when you train a supervised model kind of just on one area, it's going to overfit to that area. So SSL can kind of be a way to avoid that. So we can kind of say here that SSL pre-training, it does learn transferable bathymetric features without labels for the encoder. It shows a consistent improvement across all the new domains, the stuff that don't have labels. And then we can also say that it allows a model to be trained on labels from one site, and now we can better use it on new unique areas without having to then add, because the alternative is you'd have to have labels from all the sites, and you could do that, and I would expect the gap between SSL and the supervised method to drop, but the thing I want to show here is that we can now take the amount of labels we need and use far fewer. And to better support that claim, I want to kind of, like what I just showed is we can get better results using the same amount of Louisiana labels. What I want to see is, can we get comparable results using less labels? So I kind of just did a quick experiment here where I kind of used the frozen self-supervised learning encoder that we got from the SSL phase. And I want to see if we give a baseline model, a supervised model, 100 tiles from Massachusetts to train on, 50 Massachusetts tiles to validate on, at that point we can expect it's going to do good on the Massachusetts data using those 100 labeled tiles. I want to see, can we use this self-supervised learning model to get comparable results using only one of the tiles? So that would be like a far fewer, if we're able to accomplish that, we could save a lot of time with the amount of labels that we need. So that's kind of what I did here. What I did is I have that baseline method model trained specifically for Massachusetts, and it did do good. It got 96% accuracy. Then what I did was I took the self-supervised learning model and I had just the one Massachusetts tile that I picked, and I kind of fine-tuned it slightly based on that one tile to kind of nudge the decoder to better align with that distribution of data. And what I was able to find is that by doing that, I was able to get comparable, in this case, even slightly better performance using that model. So from that, that's promising. It shows that you can potentially get comparable results using 99% fewer labels. Some issues with the data sets, like when we saw Hawaii, it's very simple. There's not a lot of variability in it. So I kind of want to take a look, go back to that tile we saw at the start that was kind of confusing, that had a lot of noise in it, and I want to see how the model is able to work on that tile. So again, at the top, we've got the labels from NOAA, the ground truth classification, and then we have at the bottom what my model was able to predict. So it's good in that it is able to avoid that kind of cluster of noise. So we can kind of make a guess that it's able to have some kind of meaning for bathymetry there. But overall, it was much less confident on this tile. And again, that kind of goes back to the fact that these harder tiles are less represented in the data set. So that's kind of a challenge with this work. Ideally, you'd want a data set of the hardest stuff so that the model sees that all the time. That being said, even though the model seems to have missed some points here and it started to kind of classify some noise at the bottom as bathymetry, it still got the overall shape. So I would argue that it does show promise. If we could get more tiles like that, I imagine better performance could be obtained on these.
How labeled these?
Well, all of the data sets are labeled in different ways. This one, they start off with an automated some kind of algorithms to do it, some statistical methods, I believe. I don't think they're using machine learning. After that, they'd have people go in manually to correct it. But from what I've seen looking at the data, I don't know if that's always the case. I've seen a lot of points that are classified wrong. So, then kind of to wrap up soon here, this is just something that I thought was interesting. I was kind of curious what else the model is learning. You know, we can kind of see here that it is learning features useful for detecting bathymetry. But as I was kind of like visualizing the embeddings, I started seeing smaller clusters kind of distinct from noise and bathymetry. And I was kind of like wondering what that was. So I did like a quick visualization here on a tile where I saw that smaller cluster of points. And what I did was I embedded all the points in this point cloud. So you have an embedding for each of these points. And I selected, my theory was that it's maybe kind of encoding structure for some kind of object. And so I selected a point from the boat. And what I did was I looked at the 100 nearest embeddings, because you can measure distance in 3 dimensions, but that logic also holds true for the higher dimensional embeddings. And what I found was that it was seeming to move the points of the boats closer together in embedding space. So I was pretty excited to see that. I can't claim yet, this is all I have, I just got this recently, so I can't claim that it's learned what a boat is, but it's at least clustering objects above the water surface together. So that kind of shows that it's learning meaningful structure in the data. And I'd love to look further into that later on. So some example downstream use cases with some different things we could use this for. The first being kind of the identification of tiles that don't have any bathymetry or not, because if we're able to say identify, as Noah gets a new data set in, if we're able to identify that 30% of the tiles in this data set don't have any bathymetry, we could then at that point discard those tiles and potentially save an equal amount of time, say like 30% of time. Additionally, again, going back, they use algorithms to initially get the classification labels for the point cloud. I would say this could assist with that. You could use it to kind of get like a pre-screening of what it thinks each point is. And you could see how that aligns with the algorithms that they use. But additionally, you could use this as a way to kind of test the agreement between what the manual annotations are and what the model expects. If the model is running it's kind of working to embed the points, and it finds something it's not confident on, that could kind of act as a way, the model could flag that for further review by a person. And then again, going back to that tougher tile, I think a promising direction for this work would be using it to identify tiles that have more value to the model, because a limitation of my work is, again, a lot of the tiles might look similar to each other. They might be from similar locations around each other. So if you have like, if 80% of the tiles look the same, that's not going to be good for the model. It might just learn to focus on that kind of structure. So you could use this to kind of identify those unusual tiles and add them to the data set, And opposite of that, you could use it to identify tiles that are close together in distance. And at that point, you could start removing some of the redundant data. So I think that would be interesting to look at as well. So to kind of finish up here, SSL can be used to learn bathymetric embeddings that help with that downstream task of classification. And it can be transferred between different tasks such as segmentation and classification. It does improve generalizability when the labeled data is limited. You could argue that as we give more labeled data to the supervised model from different areas, we can expect the gap will shrink for sure, but we're able to get similar performance using far fewer labels. So that is a way that time can be saved. And again, that's kind of supported by the one-shot learning where I'm able to kind of nudge the decoder of the model using just one Massachusetts tile to better align it and get comparable results using far fewer labels. Some future work with this, while I did use DGCNN, there are some slightly newer models that can get, on benchmark data sets, they can get slightly stronger performance. It's unknown if they would do better on bathymetry or not, but I would specifically like to look at the sparse residual UNet because that's, from what I've seen, that has been done with contrastive learning on general three-dimensional point clouds. It just has not been applied to bathymetry. I did some testing with if intensity would assist by adding that as a feature to each point, if that would assist with the results. And initially I found it wasn't the case, but I would like to do some more research to see if I maybe normalized it differently across different domains, if that could be a beneficial feature. Again, better fine-tuning data set, different structure in the data would be ideal, and a way to kind of identify which tiles should be in the data set and should not be. And then again, I only used 4 survey sites here for the SSL phase. The real benefit here is that we can use the unlabeled data for training. So at this point, it's really easy to scale this workflow up. We could use many more unlabeled point clouds. And I would expect as we do that, the model would improve. Finally, one other thing I'd like to work on in the future, some additional experiments to better quantify the time savings and the impact of this work. So that's it. Thank you. You can go into the questions.
Thanks, one thing that always concerns me about LiDAR data is it's never quite clear how much processing has been done on various data sets before you get it.
Yeah.
I'm wondering how much that matters for the models, how you control for that. Just looking at that Hawaii data, it just looks like somebody went through and did something.
So that's definitely a good concern, because if all of your data sets are processed in the same way, then you might get data coming in that's processed a different way. And then who knows if it'll be able to generalize to that or not. I would say probably not. And so again, I am using 5 different data sets here, and NOAA does have some metadata on each data set on how it's processed. It's unfortunate it doesn't give like a really good idea. It's just a vague kind of description of how it's done. But from what I've seen, like the Florida one, it's processed by NOAA. But then later on with some of the other data sets, they're processed by contractors. So there is variability in the way the data is processed. And so that's a way to kind of mimic what we can expect in the real world.
So it is potentially a concern about the transferability.
Yeah. I would say as you add more data sets in, that concern could lessen, because there's more chance to see more data processed in different ways.
Building on that, do you think it's better to have a model that's trained on each particular kind of processing workflow and sensor, or is it better to kind of push towards some sort of generalizable model that's all purpose for all of them?
Yeah, I mean, it depends on what you're trying to do, but if you could line up a model, I guess the problem is that like you then have to build a data set of each different processing pipeline, which could be difficult. If you were able to do that, maybe it could be better, but there's also an argument that by seeing data in different ways, it can actually use information from those other areas and apply it to the different data sets. So I can't say for sure on that, but I think it is simpler to have a model that can generalize to any area.
Could you please repeat what does the baseline mean?
Yeah.
Versus SSL.
Yeah, so in the segmentation, the baseline versus the SSL model you're saying? Yeah. So the baseline and the SSL model both are the exact same architecture. They're both the DGCNN neural network. The baseline, it is trained specifically for Louisiana. It's trained on Louisiana tiles, validated on those tiles, and then it's tested on all 5 areas. So you have that versus the SSL model, which is you're only training the decoder on the Louisiana tiles. So the main difference between the two of them is the training strategy that is used, if that makes sense.
The level of success you measure against law or contractors' classification.
I compare.
What is true and what is.
I compare to the labels given by NOAA.
And we know that it's very dodgy.
Yeah, that's the thing. They are. When I looked at it, there was stuff that was wrong. So what I ended up doing was I went through all of the tiles manually and looked at them to make sure they looked correct as well. In addition to instead of just blindly trusting the labels.
They look correct in what sense?
I did a visualization in three dimensions.
So the whole time.
Yeah, for all of the labeled data sets. I looked
If
at
you
them
can
all.
go back to slide 30, that was the sketchiest one shown in Massachusetts.
And sometimes I look at those tiles, and sometimes like whole
Yeah.
tile, and one point is water, everything else is unknown.
Yeah,
Just
Yeah.
unidentified.
That one's scary.
For sure. Not
Yeah.
Because there's
Well-
lots of like points marked water noise that look really close to the seafloor.
It is pretty
There's also
close
water
like that.
there.
Yeah.
The fact that there's nothing in between is what scares me.
When you do look at it in 3 dimensions, I would say it looks less concerning because you're kind of seeing it in 2 dimensions here, but it is still it can be really difficult to extract the.
So what's the something that mixes up with the bathymetry?
But-
Blue dots that are interspersed with red ones.
By that you mean
Yeah, well, in this case, this particular case, why blue is mixed with red?
that's based off of the NOAA classifications. If you look at it in
Well,
3
that
it
is
strays.
good logic.
Yeah.
So is that what you corrected? Correct that?
Yeah, when you look at it in 3 dimensions, though, it does line up more with what you would expect.
Most likely, it's everything.
Yeah, it could be.
On the other hand, quite often there is a vegetation
Yes.
which looks like bathymetry because it's connected to it. So when you're clustering, it definitely will belong to the same cluster because of the proximity.
Yeah,
But on the other hand, it's not bathymetry.
that's yeah. It would have been nice if I haven't seen a tile where I've been able to identify
can
vegetation
show
in
you
it,
later.
but I imagine that is a difficult thing that the model could be struggling with, is kind of differentiating between bathymetry and vegetation like that.
This is where I think it would be helpful to start bringing in some of the other things beyond just X, Y, Z, where we have like
Yeah.
return number, right?
Well,
Yeah.
this is not provided anymore on the regular basis.
Yeah, return number, intensity, they're a standard part of the data sets of a lot of our tiles.
Oh, yeah, there is no, full, rate.
This one, just to provide some insight, this is a data set that I worked with at NOAA's request. And I mentioned it to Joe, and Joe bravely took it on. And it's an area around Gloucester, Massachusetts, where there's a number of sand flats that when the tide goes out, it's dry land. And then when the tide comes in, it's wet. And when they fly these LiDAR tiles, they go up and down, booster-photonic pattern that can be over a period of 3 to 5 days. And so some of what may be going on here as well is that some of this data was collected at low tide and the area looked dry, and then the other
Oh, yeah.
was collected at high tide.
Explanation.
It's,
Supposedly the case.
this is a hard one, so it's got some nasty things.
So that's why.
That's a good data set, it's not a bad data set.
You're right, it's typical, it would be typical.
So that's why the number, like the profile number or whatever, would be meaningful. I was trying to sort out, like, that would tell you that 2 points were collected, not adjacent to each other in time.
Yeah.
Application. Yeah. Could you go back to your slide where you lay out the different data sets and the processing pipeline?
If I can find it. Yeah, this one?
Yeah, that's the one.
Yeah.
In the training of the SSL bit, is that being done sort of sequentially through each of those as you pass through the data sets? Or is it done a priori before you even start? You know what I mean? Like, is it improving as you go through the?
Well, the way it's done is I combine those 4 into one large data set. So you do the self-supervised learning on its own at the start.
Okay.
If that answers your question.
Yeah, so you have that pre-trained and it's fixed, and then you go through the data set separately.
Yeah.
And do the fine tuning.
Yes.
Why don't you choose to only fine tune on Louisiana? Because you have train fine tune on Louisiana, and then the rest are tests. Is that?
I picked that one just kind of based on looking at it. Not very scientific. It would be good to have testing it on all of the different areas as well, but with time constraints, I was unable to do that.
Would you be able to fine tune on Florida, Hawaii, and Maine as well, and then only use Massachusetts as tests? Would that make sense? Or
Yeah. You could. What I would hope we see is that you can train instead of using any of the labels from Louisiana, you could train on Florida or something like that, and using self-supervised learning, we could hope that it would be able to generalize good. I would say with the Hawaii one, though, with how simple it is, you probably would not want to train on that one because it just has to learn super simple hyperplane cutting through. Because you always have that pretty large distance between the surface and the bathymetry.
When you're looking at different locations, we cannot really expect that the structure of bathymetry is that too different. You know, of course, there are different currents and different tides, but still, the law of physics of fluid mechanics dictate that there are more or less the same. So
Yes.
I suspect that the difference comes mostly from the way how the data was collected and what has been done with this data afterwards.
I would definitely agree with that. That makes sense to me.
And that returns back to your suggestion that maybe there is no reason to generalize movement, but concentrate on previous pipeline.
Are you saying
Or-
that things like water quality don't have, like water clarity don't have an impact?
Well, of course it does, but it could happen anywhere.
More likely to have a different.
Yeah.
Different
I guess
biome.
Hawaii is so clean.
What does it matter if you have something at 30 meters or 2 meters? The rules are the same, it's just the filtration is different. And so density of points is different, right? But even if it looks pretty much the same.
I think the problem is that if you use a supervised learning baseline on something just, well, I mean, we saw it with Louisiana, if you train it on that, it only is shown labels of bathymetry that is a few meters deep. So it kind of latches onto that shortcut. It's like, okay, all bathymetry, or it could potentially latch onto that shortcut where bathymetry is at a certain depth. And because it then hasn't seen anything on Hawaii, like we're not hard coding the rules ourselves, it's learning from the data. So then when you move to Hawaii, it'll see bathymetry at a depth that it's never seen before, and that's where it can fail. It may be relying on a rule that does not hold true to the other area.
I think you sort of showed, I mean, my recollection is that the performance on the Hawaii data set is not spectacular. I guess
Yeah.
not 100%.
If we trained directly on Hawaii, we could expect it to be good, but
Or
of
if
course
you
we didn't.
trained a little bit on Hawaii.
Yeah.
It might have.
I think, this is the last question or one more after this.
I really enjoyed your talk. I know nothing about this area, so this question might be very naive. It seemed like your model was trying to do things point by point. Like each point, you had features about the direction of the 20 nearest neighbors. My intuition is sort of that you were learning about smoothness, for example.
Yeah.
Whereas I would have naively expected that, well, the ocean is going to smush everything around. The bottom of the ocean is going to be kind of smooth. Is there a reason you didn't try to take advantage of that assumption in your model architecture rather than learning about smoothness as part of your training process? Like, why not just try to fit a mesh to the data or something that we know is going to be smooth?
Yeah, I mean, that could be another approach, but I think I'm not sure exactly how fitting a plane would work, but would that require, or yeah, mesh, would that require some kind of, would you have to, my question is, would that generalize to other areas, do you think? Or would you then, when you get to a new site, have to tune that kind of plane fitting?
It won't, because, we've seen so many examples with the canals,
Yeah.
artificially made channels, and so there is no plane.
Well,
So-
but I think maybe it's not just a straight plane, but like to have kind of like a flexible mesh that kind of like, I mean, the question is like, what is the goal of, like, why are you even doing this whole bathymetry thing? Like, why do you care which points are bathymetry? If you want to know, well, what's sort of the depth, if you want to have kind of like a mesh of what the ocean floor looks like, while modeling the fact that there's an ocean floor, that this is like ultimately sort of like a somewhat like smooth structure could be like useful, but maybe this is like what would come after what you're doing. So maybe you're just
Yeah.
focusing on the denoising, that'd be the next step. But sometimes if you know what the downstream application is, doing the denoising for the downstream application or
Yeah.
with that in mind might actually help you, like the way that Vito said, like you kind of like, there are actually more constraints that you're currently not taking advantage of.
Yeah.
Like in your case, bathymetry could look like this. It's a possibility. And you just say, well, machine learning, tell me what it is. But if you actually, as a human, know it must be something that is kind of like more smooth.
Yeah.
Your machine learning can help, or it can be helped by embedding that assumption.
Yeah, I think that would be something that would be interesting to explore further.
But of course, if you're trying to classify seafloor vegetation, now that's not going to be a helpful assumption.
Yeah.
But one of the things that we wrestle with NOAA is what do they want these data for? And a lot of it is coastal erosion, coastal resilience. And so the idea of a mesh, that works just great for that because that controls the dynamics of a lot of things. But if it's used for navigation, they need to know where the
There's the one.
masts of sunken ships are. And so in that case, they actually need to know every single point. And so that's one of those things that when you talk to Noah and say, what do you want to use this for? The answer is everything. Okay.
But I think the application here is we've got a lot of algorithms like chart and cube that'll take sonar points and get out a surface.
Yeah.
But when you get a LiDAR cloud and you have this water surface above it, that throws the whole thing off. So just being able to take that out. And that kind of was one of the things, we can discuss it later, but I wonder if you want to actually train it to recognize the water surface as well.
Which
Right.
is also
Definitely.
very difficult because you have the different flight lines, which may have different level of tides. I've seen plenty of examples when water level, water is here and there in the same time.
Yeah.
So I wonder, like, I'm assuming it makes it harder, but do you get better performance if you try to train it multiple labels instead of just a binary is
Definitely.
bathy, is not? If you say is bathy, is water, is noise, is something else.
Oh, that's
I
what
have
one
been-
does.
Yeah. Having the extra like noise labels as well, like I think that could definitely help. I would love to have that, but not all the data sets had that in it. So probably have to find a way to manually get that.
Right. I think we'll wrap this up. So I will just thank you all for your presence, your very good questions. Thank you very much, Joe, for your presentation.